Hello, my name is Hendrik Brückler, and this is the 3D motorcycle complex for structured volume decomposition, a joint work with Ojaswi Gupta, Manish Mandad, and Marcel Campen. To begin with, let's start with a short overview of what the motorcycle complex actually is and what it does. The motorcycle complex partitions a volumetric object, for instance a TED mesh, into blocks. The partition, however, is not arbitrary. As an additional input component, we require a certain volumetric parametrization, called seamless parametrization, which is usually obtained from frame field-based approaches. Given this parametrization, we can ensure that every cell of the partition is an axis-aligned cuboid under the parametrization. Conceptually, the motorcycle complex can be understood as a generalization of motorcycle graphs on surfaces to the volumetric setting. To understand the motivation behind this, let us first revisit the 2D case of motorcycle graphs. The name of the concept actually does not originate from a purely scientific context. Instead, the name motorcycle graphs was inspired by the movie Tron. The plot featured a racing game between motorcycles that left impassable traces behind them. This concept was later formalized by Epstein and colleagues. Given a set of particles with initial positions and velocity vectors in the 2D plane, the motorcycle graph is defined as the union of particle trajectories, assuming particle traces to block other particles. This graph structure was later lifted from the 2D plane to 3D surfaces for several scientific applications. For example, Epstein and colleagues constructed motorcycle graphs on quad meshes and used the partition to determine isomorphisms between different meshes. Later on, Miles and colleagues used motorcycle graphs on triangle meshes equipped with cross fields and employed the partition to compute seamless parametrizations on the input. The application most important for us was by Campen and colleagues, who used motorcycle graphs on surface parametrizations to generate quad meshes. Given this success of motorcycle graphs in the surface setting, let us consider the transfer to the volumetric context, which we are concerned with here. Consider a surface, as shown on the left. Inscribed in red color are so-called singularities, a set of special, isolated points. There are two important things to remember about singularities. Firstly, they are prescribed by a pre-computed directional field on the object. On a 2D surface, these fields are called cross fields, and they define a fourfold rotation symmetry everywhere except for the singular points. Those may, for example, exhibit a 3- or 5-fold symmetry instead. The second takeaway is that a parametrization conforming with these singularities has a corresponding number of isolines incident on them, as highlighted in the picture. These isolines are called separatrices, and tracing them across the surface yields the motorcycle graph. Junctions between traces are points, and the cells of the partition become rectangular patches. Let's now take a look at the volumetric setting. Here, singularities are not points, but form a network of curves. They originate from octahedral fields, also called frame fields, and singularities are curves around which symmetry differs from the octahedral one. Consequently, a volumetric parametrization has isoplanes incident on these. We show in the paper that the logical extension of motorcycle graphs to the volume then looks like this. Separatrices must be walls, junctions between them form curves, and the cells of the partition are cuboid blocks. Let us now highlight why this generalization is such a valuable thing. Just like motorcycle graphs were used in robust quad mesh generation, we will show how to use the motorcycle complex for robust hex remeshing. Furthermore, the motorcycle complex can be employed for the structural optimization of hex meshes. Earlier work by Gao and colleagues used a similar but much finer volume partition for that purpose. Instead, using the motorcycle complex promises advantages in both efficiency and flexibility, as we will show later. Lastly, the partition obtained by the motorcycle complex can also be used in the construction of solid T-spline spaces. For now though, let's take a more detailed look at hex remeshing. Many hex remeshing methods can be assigned to one of three algorithmic classes: those based on grids, those based on polycubes, and those based on seamless parametrizations. All of these have strengths and weaknesses in different aspects. Grid-based methods tend to not do very well in terms of feature and boundary preservation, and provide rather limited structural flexibility. However, they are the most robust hex remeshing methods out there. Polycube methods are somewhat of a middle ground. They perform reasonably in all of these three aspects, but don't excel in any of them. Parameterization-based methods, on the other hand, are best suited for the tasks of feature preservation and provide maximum structural flexibility, at least in theory. In practice, their application is hindered by robustness issues. The motorcycle complex, as we will show, can be used to significantly increase the robustness of these approaches. But how is that? Let's take a look at the pipeline for hex remeshing based on parametrizations. The input, in general, is a tetrahedral mesh. On that mesh, a volumetric seamless map is constructed. Here, we only show a 2D visualization for simplicity. A seamless map is one for which parametric grid lines are parallel when mapped onto the object, even across cuts. Note, however, that the grid lines need not be continuous. This is achieved in another step called quantization, in which the grid lines become continuous and singularities are assigned integer coordinates. This results in the grid lines forming a structured mesh on the object. This integer grid is then extracted as a hex mesh. Hex extraction has already been very robustly solved by Lyon and colleagues. The seamless map generation step is more intricate, and a lot of research was and is still being conducted on finding robust solutions. The quantization step, however, has been neglected since its first treatment by Niese and colleagues. In their paper, the authors suggest greedily rounding the relevant coordinates. However, this approach is prone to produce rounding conflicts, which eventually lead to defects in the output. Now, how can this be circumvented? Our approach is to construct the motorcycle complex on the initial seamless parametrization. Using the obtained partition, we derive optimal integer dimensions for each block and then perform the quantization blockwise, thereby guaranteeing to obtain a valid quantized parametrization, from which a hex mesh without defects can be extracted. Now that the motivation is fully clear, let's focus on the construction algorithm. As input to our algorithm, we take a seamless parametrization on a tent mesh. As a first step, we have to ensure that the input is actually truly seamless. Typically, the output of parametrization generation methods is seamless only up to some tiny numerical inaccuracies. Extending a method of Mandad and colleagues to volumetric parametrizations, we are able to fix such numerical issues. On the sanitized input, we then construct the motorcycle complex in 3 steps. First of all, we trace walls through the volume. These partition the volume into cells. Our analysis shows that the resulting cells can be more complex than a simple cuboid. However, it turns out that even such complex cells can always be simplified by introducing additional walls. Finally, we find regions where the number of cells can be reduced by merging cells, so we perform this reduction as well. Notably, our algorithm works just as well on hexahedral meshes. The tracing of walls can be divided into 3 components. Initially, we spawn walls at singular edges, expanding them along all incident isoplanes until the expanding wall hits a boundary or another wall. Let us first consider tracing in the 2D case. Here, we start from singular points and extend rays along isolines. We keep extending these until a collision is encountered, which is a local instantaneous event and causes one trace to stop in a T-junction. Again, the remaining traces proceed until they collide as well. Based on that, we can imagine a simple 3D example obtained from the 2D case by extrusion. Singularities are now parallel lines from which walls emerge along isoplanes. These walls again keep expanding until there's a collision, which now is no longer local, but still in sync along the whole intersection curve. Again, the remaining walls keep expanding until they collide as well. On an actual mesh, this simple case can look like this. Starting from singularities, walls are traced and form simple T-junctions where they collide. The resulting partition is in essence simply an extruded motorcycle graph of a surface. But in general, things are rarely that simple in the volumetric setting. Here, singularities are no longer all parallel, but may be perpendicular. Accordingly, the expanding walls can have 3 different orientations. It is then clear that for some pairs of walls, an all or nothing collision event is no longer well defined. Instead, we need to model collisions as a fully local event, allowing walls to be partially blocked and to partially proceed, flowing around their dynamic obstacles. The resulting partition then is also more intricate than in the extruded case. These configurations are actually the common case and not the exception in 3D. Here, partial obstruction and intertwined walls are well observable. Taking a look from yet another perspective, we see how complex the interactions can actually get. It is also obvious how efficiency benefits from stopping walls already when they meet other walls. Imagine on this singularity structure a conforming volume partition that would let all walls continue through to the boundary. That partition has a name, it is called the base complex, and we will later show how much simpler the motorcycle complex is in comparison. Despite wall configurations being quite complex in the 3D setting, through a theoretical analysis in our paper, we are able to determine universal properties of the partition. First, consider the types of junctions that arise where walls meet along a curve. Because walls are coordinate isoplanes of a 3D parametrization, we know that they meet in 90-degree angles. Cases like those depicted on the far right cannot occur, as that would imply that a wall had stopped without having been blocked. Based on this, we can enumerate all possible corner types in regular regions of the parametrization and show that these corners again form solid 90-degree angles. The same can be shown for corners along singularities. Based on these observations, we show in the paper that all blocks are either of cuboid or torus type. However, we can simply transform a torus into a standard block by inserting another wall. Another important property of the partition is its non-conformality. Not only can the edges of a block be composed of several arcs of the complex, also the faces of the block are commonly made from several patches. Lastly, after tracing, the complex is not locally minimal. That means we can find some adjacent blocks of the partition that when merged together still form a cuboid. We suggest performing this reduction in a greedy manner to further simplify the complex. Let's also take a quick glance at a possible implementation. To simulate walls expanding simultaneously in a space and time discrete setting, we use a priority queue that holds mesh facets. These are ordered by their distance from spawn, meaning walls that have expanded least far are always propagated first. We start by tagging all singular edges as blocked, then for each incident isoplane, we retrieve the corresponding mesh facet and insert it into the queue, with an initial distance of 0. For the tracing part, we repeatedly retrieve the facet with least traveled distance from the queue, mark it as blocked, and proceed to expand over all of its unblocked edges. We block those edges as well and insert the next isofacet into the queue again with priority lowered by a distance delta. So far, we have silently assumed that isoplanes always coincide with facets of the mesh. This is of course not the case. However, we can refine the mesh on the fly. In each expansion step, we check whether the isoplane coincides with a facet. Then, we simply use that facet. Otherwise, we split a tetrahedron so that the isofacet we need is created. In practice, our final implementation then looks as follows. In the parametrization-based setting, the fronts of wall expansion are not smooth. However, that does not affect any properties of the partition. Here, we also see the process of reduction. It is rather obvious how beneficial it is to the simplicity of the obtained partition. Now, let's evaluate this simplicity. As mentioned before, we can consider the base complex, that is, the conforming volume partition that is formed by the complete set of separatrix isoplanes. Due to the similarity of the two partitions, we evaluate our results in comparison to the base complex. The motorcycle complex in general is much coarser, and for that reason can be computed and used for subsequent applications much more efficiently. On a dataset of Hex Remesh-induced parametrizations, the motorcycle complex is, on average, 5 times coarser than the base complex. For extreme cases, as shown on the right, it is even up to 100 times coarser. Looking at absolute numbers, it is also evident that this is of practical relevance. Only about 3,000 blocks in the motorcycle complex, in contrast to almost 500,000 blocks for the base complex. On another dataset of frame field-induced parametrizations, the motorcycle complex is 4 times coarser on average, and for extreme cases, even up to 30 times coarser. But now let's consider again the application of hex remeshing. Given our non-conforming partition of the input, the task is now to transform the underlying seamless parametrization into a quantized one, with elements aligned to integer coordinates. Doing so, we want to ensure to minimize deviation of the quantized map from the original one. We use the partition to perform the quantization in a global manner and avoid any degenerations. To that end, we have to enforce that all patches of the partition stay rectangular and all the blocks stay cuboidal. This corresponds to an integer quadratic problem of assigning integer lengths to each edge of the motorcycle complex. Our experiments show that these instances can be solved efficiently with a general purpose solver. Given the resulting integer dimensions for each block, we essentially rescale the parametrization within each block to assume the prescribed integer dimensions. So, here is how that approach performs at hex remeshing. As you can see, we are able to produce hex meshes of very finely varying density and up to rather coarse resolutions without any defects. Noticeably, this is guaranteed to work on any valid input. Now, how does our approach compare with the rounding method we promised to improve on? For fine target resolutions, the hex meshes from our method are on par, quality-wise, with meshes produced by a rounding-based method. As the target edge length increases, our method still reliably generates valid hex meshes, while rounding is bound to introduce defects that even mesh extraction by hexex was not able to repair here. Even for the coarsest possible target resolutions, our meshes are still valid, while meshes obtained by rounding are beyond broken. On the dataset of frame field-induced parametrizations, our method is able to produce 2.5 times coarser valid hex meshes, with extreme cases even reaching up to 20 times. Another interesting comparison is that between a quantization of the motorcycle complex and one on the base complex. In this diagram, we see the actual output resolution for an example model on the y-axis, plotted against the target resolution on the x-axis. Ideally, there is a linear correlation between the two. The base complex quantization can only control the target resolution in a very coarse-grained manner. The motorcycle complex quantization, in contrast, follows the linear relation much more closely. In order to understand this phenomenon, we look at what the quantization actually does. It decides on a number of hex layers to insert between two corners and propagates that choice through a whole layer of blocks. The base complex in this case allows for only 2 different choices of layer insertion. The motorcycle complex instead allows for a whole 11 different choices, due to its T-junctions. This explains the much higher flexibility in achieving the target hex mesh resolution. Finally, let us also talk about possible extensions of our work. The first interesting aspect is that of minimality of the partition. A theoretical question of interest is how close the motorcycle complex as obtained by our method comes to the theoretically coarsest partition of the input. Another, more practical question is what kind of heuristics could be applied to the tracing and reduction order to achieve even coarser results. The second interesting aspect is that of considering other types of input. One such input may be hex-dominant meshes. A similar consideration would be whether the motorcycle complex could somehow be constructed even on parametrizations with inversions or degeneracies, which is of high practical relevance. Lastly, the quantization procedure in the state presented in our paper is somewhat limited. For 2D motorcycle graphs, however, it has been shown that quantization flexibility is important for structural optimization of the output. We have a paper coming up later this year that treats the fully flexible and robust quantization in detail. Thanks for your attention, and feel free to also check out our paper or its implementation, which is available on GitHub.